Okay, now let's look at the magnetic field of a long straight wire. This will be our final application of the right-hand rule. Well, let's first see, we've already seen this, that, well, we actually haven't seen this, but it's been sort of implied, and that is that a current in a wire creates a magnetic field that surrounds the wire. And actually, when we have a current within a loop of wire that sits in a magnetic field, what causes that loop of wire to feel a torque, as we've seen before, is the interacting magnetic fields. So there is a magnetic field due to the permanent magnet, and then the current in the wire, which is moving charges, also generates its own magnetic field. And you have these interacting magnetic fields that cause this loop of wire to feel a certain torque, as we found before. Now, to find the direction of this magnetic field, we're going to use the right-hand rule. We'll let the thumb of your right hand go in the direction of I, in the direction of the current. And then your fingers wrap around to give the direction of the magnetic field. So, for example, if we have a wire that's like this, we let our current is in this direction. Our thumb will go in the direction of that current, and then our fingers wrap around to give the direction of the magnetic field. So, say for example, we have this wire. Pardon me. Say for example, we have this wire. It has a current I flowing through it. I would let my fingers and my thumb and my right hand go in the direction of the current, and then my fingers would wrap around, so that we would find that on the right-hand side that the magnetic field would be into the page, and on the left-hand side the magnetic field would be out of the page. You let your thumb go in the direction of the current, your fingers on the right-hand side would go into the page, and then they would wrap around behind the wire. So behind the wire, the magnetic field would actually go to the left. In the front of the wire, it would actually go to the right. I have a little video here that was produced by the same guy that does the Veritasium videos. He describes this. This rule is called the curl rule, I think. It's the right-hand curl rule. And he describes how it works. And he actually shows with a compass how you can measure out or map out the magnetic field around a current carrying wire, and how this is shown by the right-hand rule, the curl rule. So you can watch that here. It's just a few minutes long. Now I can also calculate the magnitude of this magnetic field. So the right-hand curl rule will give us the direction. We can also calculate this magnitude. It's given by the permeability of free space, mu naught I over 2 pi r. All right, where r is the distance from your wire. So if I have a wire here, and I want to know the magnetic field out at this point, this is the distance r. I is the current. Mu naught is 4 pi times 10 to the minus 7. If you remember, we found this earlier. It was related to the Coulomb's constant K. Or no, I'm sorry, never mind. This is the permeability of free space, and we use it to find B. All right, so now let's find the, you can try these quick tests where here you actually have two wires, and you want to find the direction of the magnetic field from each of the wires, and I want to know what is the magnetic field here at this point. What is the direction of the magnetic field? In this one, you have 4 different wires, and I want to know what is the direction of the magnetic field at the point P, or rather, which one of these has the largest magnetic field. I'll do this first one for you, and then you can try the others. I want to know the magnetic field at this point. So due to this wire, where the current is coming out of the page, the magnetic field is in this direction. Due to this wire, where it's coming out of the page, I let my thumb go in the direction of the wire. My magnetic field traces around in this direction, so at this point, it's in that direction. Similarly, over here, out of the page, magnetic field goes in that direction. So it's there, tangent to that circle. And let's see, I have one more right here. My magnetic field goes in this direction. So at this point, it's in that direction. So the net magnetic field here, because these vectors are all the same magnitude but opposite directions, is going to be 0. So obviously A is not the answer. It doesn't have the largest magnetic field, doesn't have any magnetic field at all. So now you want to try out these other two and find out which of them, or maybe they all have 0 magnetic field, which of them has the greatest magnitude. We will pick back up with this in a few minutes.